Okay, so this is the practice internal for simultaneous equations. So what we've got is we've got a student Mele who's spilt coffee on her homework. One of the equations, we're not sure what the terms for x, y, and the constant are. So she decides to represent the missing information using variables f, g, and h, shown here. And then she thinks she remembers the values. So we've got two cases here, and we've got to do each of them. Alright, so for this first one here, so the three equations are, what I'm going to do is I'm just going to put it in a table just so it's clear to me where my answer starts and where the question is. Okay, so the three equations are now instead of f, we've got 2, instead of g, we've got 4, and instead of h, we've got 0. Okay, so we could solve this by hand, or we could also solve it using GeoGebra. So if I open up a tab, geogebra.org /CAS, what that's going to do is that's going to open up the equation solver. Right, now what we can do is we can copy each of these three equations in. I'm going to call my first one equation A. I'm going to call it that. My next one, I'm going to call equation B. Equation B is that. And finally, equation C. Equation C, we're going to call that. All right, now I'm going to write solutions, not solution, solutions, square bracket. So as you can see there, we're doing solutions and then the list of equations and the list of variables. So solutions, we do the square bracket. We're looking at our equations A, B, and C. And then comma, these squiggly brackets. The solutions that we want are X, Y, and Z. Okay, so let's see what happens. Press enter, so we get the solutions, or sorry, we get one solution that is at the point 17, so X is 17, Y is negative 25, and Z is negative 13. So what I'm going to do over here is I'm going to change this to 3D graphics. I'm going to get rid of this screen. Rid of that. I'm going to change the color of these just to help us see what's going on. Oh, this one. Okay, so what we've got is at the point X is negative 17. So let's zoom out a bit more. Okay, so X, so the X must be this green one here. So X is negative 17, Y is negative 25, and Z is negative 13. So you can see that they intersect at a point down in there. So the point they intersect is this point in here. So that is where they intersect. If you want to turn on to check what each of the axes are, if we click that settings cog, then we change the labels to X, Y, and Z. We can then see, so x is negative 17. Sorry, x is positive 17, so x is all the way up here. Y, which is this one here, y is down negative 25. And then the z is negative 13, so it's down on this blue axis down here. So that is where our solution is. Okay, so what I'm going to do is I'm actually going to take a screenshot of this. I'm just going to put it in here to support my answer. So I'm going to say using the GeoGebra solver, there is a unique solution to the equation. So that means there's just one solution and then the solution is at 17, negative 25, negative 13. So 17, negative 25, negative 13. Alright, so that is the first case done. Alright, now the next case. Let's set another table because that helps you understand it a bit better. So I'm going to say, so the three equations, so we can change it to three equations in this case are, I'm going to change this one as well, three equations in this case. So I'm just going to copy these three equations, and then like I did for that first one, I'm going to change the variables f, g, and h to 1, 4, and 25. Now 1y, I'm going to try it like that. Okay, so the three equations are these three equations. Oh, sorry, I've been looking at the wrong screen. So what I did is I wrote the solution at that point, I pasted it in, and I've just started on my second case. Okay, so I'm now down to this case here. Okay, so what I'm going to do is I'm going to use the GeoGebra solver again. Now I could do it by hand, but I'm going to use the GeoGebra solver to save some time. And that's all that is actually required to show. So we're actually more focusing on explaining what's happening rather than the algebra behind it. But I know you guys know how to do the algebra anyway. Alright, so what we're doing is we're changing the y, z, and the constant. So looking back here, we're changing the y to just y by itself. We're changing, we're leaving the 4z as that, and then the constant at the end is 25. So we actually only changed the f and the h. So we changed the f to 1 and the h to 25. Alright. Now, what's happened with our solutions, we've got this negative z plus 4, 2z plus 1, and z. So what that solution tells us is that is actually a vector line. So that is not one solution, that is a infinite number of solutions. So if I get the graph there, we can see that there is an infinite number of solutions. So I'm going to make a copy of that. Oh. And explain my answer. So all three planes of these equations intersect along a line, so there are an infinite number of solutions. So all three planes of these equations intersect along the line, there are an infinite number of solutions. And you can see that happening there. Alright, so we have answered the first and the second parts of that first. Okay, so what we're going to move on to now is part B. So in part B, we are now changing f, g, and h to any values that we want, and we're going to make a unique solution, a consistent solution that also has an infinite number of solutions. So we've actually already done those first two situations above, but we're going to come up with some other numbers. And then finally, we're going to come up with an inconsistent solution. So an inconsistent solution means there are no solutions. All right, let's actually start with the consistent and infinite number of solutions. I'm going to start with this one, and we'll come back to that unique solution a bit later. Okay, so to make the system consistent but with an infinite number of solutions, so what we're doing is we're going to change f and g and h, and these other two equations are going to remain the same. So if we go to GeoGebra, and if we just look at, so I'm going to get rid of my equation C. So turning here, just try and delete that. Okay, so what we can see is that the first two planes intersect along an infinite number of points. So what I'm going to say is, because the first two equations form planes that intersect along an infinite line. Also, because the first two equations are consistent with an infinite number of solutions, because they intersect along an infinite number of points. So, alright, let's start again. The first two equations are consistent with an infinite number of solutions because they intersect along an infinite number of points. We can make the third equation identical to one of these equations. Then our simultaneous equations will still be consistent and have an infinite number of solutions. So what I'm going to do is I'm going to change this equation by using one of these other equations. So what I can't change in this equation is the 6x. So I want one of these other equations to change to 6x. So looking at equation 2, I can make that 3x into a 6x by multiplying by 2. Multiplying the second equation by 2 gives, so we've got we've got 6x plus 2y plus 2z equals 26. So multiplying the second equation by 2 gives that. We will use this as our third equation. So let f be 2, g be 2, and h equal 26. So be answer. So I'm letting f equals 2, g equals 2, h equals 26. All right, and let's see what happens. Like I say, for my equation C, I've got this equation here, and it doesn't seem to have changed the graph at all. Now that is what we expect, because we expect them to be identical. So planes 2 and 3 are identical. So if I solve them now, we've got the solution involving z, which means that the equations are intersecting along an infinite number of points, so they're an infinite number of solutions. So equations 2 and 3 are identical and intersect equation are identical with planes 2 and 3 intersecting plane 1 along an infinite number of points. Cool. Alright, now we want the equation to be inconsistent with no solutions. Alright, now one way of doing that is by making one of the equations parallel. So simultaneous equations that have parallel planes will never intersect, and so we'll have no solutions. We can make the equation 3 parallel to equation 2 by changing the constant. So rather than 26, we could say, for example, so 26, I'm just going to say 1. So I'll just change up that spelling mistake. Okay, so we can make equation 3 parallel to equation 2 by changing the constant. So I'm just going to look at what we had up here. So the constant, rather than 26, we could change that to be, let's try to change it to be 1. So if we change it to be 1, so 6x plus 2y plus 2z equals 1. We can see that the equations are parallel. Because equations 2 and 3 are parallel, because the planes formed by equations 2 and 3 are parallel, there are no solutions to this system of equations because they never intersect. Because, or I'm going to say all three never intersect. Because equation 1 intersects with equation 2, and then equation 1 intersects with equation 3. Equation 2 and 3 never intersect because they're parallel there. Alright. So what we've got there. So I'm going to say h is equal to 1. I'm actually going to put in as well, we could have h equal to anything as long as it's not 26. Because that would make the situation above where they are parallel. Alright, now I'm going to go back to the first part, make a unique solution. Okay, what I'm going to do here. So I'm just going to try. I'm going to choose that to be, these are just random numbers. I'm choosing 2, 3, 4. So I'm going to try numbers 2, 3, 4. 2, 3, 2, 3, 4. And if I did that, look, we have an intersect at one point. So that was just a check and guess. So making G equals 2, H equals 3, F equals 2, G equals 3, and H equals 4 gives a unique solution at, what's the point? The point was 26, negative 43, negative 22. It is unique. So I'm going to say this is where the point where all three planes intersect. Cool. And now we have looked at every situation. So Mele has come up with every type of different situation that could be possible for her homework. So I think she's done a pretty good job.